He talked about, fundamental theorem here, line integrals, which we talked about last time. Called, maybe the name comes from, remember the fundamental theorem of calculus, part 2 anyway, that we really stressed, talked a lot about, but if I've got just a definite integral, the fundamental theorem of calculus says integrate, and I call it here kind of something a little different, just to gear us up for what we're coming to, but f prime of x, big F prime of x. So the of course relationship is f then is the antiderivative of f prime. That's the fundamental theorem of calculus part 2. It says, so here's what it says, what part we'll use of it. I can evaluate this by doing the antiderivative. F is the antiderivative of f prime. All I have to do then, is do the antiderivative and then evaluate that at b, and then subtract the antiderivative at a. All right. So the fundamental theorem of line integrals, that's fundamental theorem of calculus. Fundamental theorem of line integrals is somewhat similar. Suppose C is a smooth curve. Write this all out. Given by R of t, vector function, t between A and B. Also, f is a function whose gradient vector symbolized by that is continuous on C. So a few minor details there. Then, this is the fundamental theorem. The integral on C, that smooth curve, RT. So the integral evaluated over that integral, line integral. Then you have the gradient of f dotted with dr. That integral can be evaluated by simply, similar to our fundamental theorem, simply by doing f evaluated at R of B minus f evaluated at R of A. So it's similar. It's similar. Yeah, because remember, gradient, the gradient function, that is the partial derivatives. If we're talking about two, start over. Gradient of f is partial of f with respect to x, comma partial of f with respect to y. One way to do that, that's so that in a way, so hopefully you can see the connection here. That's very similar to what we got here. This is the derivative, and that's the antiderivative. Okay, two separate ways there. So that's the same thing here. F, this is the gradient of f, so same kind of relationship. But what it says is, all right, so what does it say right here? Well, to do this line integral, all you have to do is figure out, you got this is your, what you're integrating, but if you can figure out then the f, potential function, another way to look at it, then all you have to do is evaluate it at R of B, and then the F, evaluate that at R of A. In other words, plug in your endpoints there into R of B, R of A, and then plug those into F. So it's essentially the same, what we're saying here. Evaluate them at the endpoints, if you will. Okay? Maybe a little more going on than the others, but. All right. So here's our first little problem. So evaluate the integral over C, gradient of f dot dr, where f of x, y, z equals cosine pi x cosine pi x plus sine pi y minus x, y, z, and C is any path from 1/2 to 2 to 1 to 1. So this one's kind of different in that we don't have to figure out basically the integral here because we know the function is what it is, okay? So gradient of f, we can figure it out, but we're already given what f is. So we've kind of figured, they've given us here in these problems, they'll be given what the function is. Later we'll have to figure that out. But for now, for this problem, the point, I guess, of this problem is the thing here is any path. So C here, smooth curve, given by R of T. We don't know what that is. It's any path. And we just know the endpoints of that path. So wherever it starts and then wherever it ends, that it doesn't matter the path you take. We're starting here, and it could go, all kinds of ways, but we're ending at that point. Starting at this point, ending at that point. Doesn't matter the path, as long as it's smooth, okay? It does have to be smooth. So, what is this integral then over that closed path? Or that path? Well, it's f evaluated at R of B minus f evaluated at R of A. So this is our A, if you will. This is our B. Essentially, we've already evaluated R of A and R of put it this way. That's R of A, that's R of B, you see. Because that's what evaluating it means. You get a point. Terminal. The tip of the vector. So you're with me there? So how do I evaluate this? Well, I just do f of the terminal point, 2, 1, negative 1, minus f of the initial point, 1, 1/2, 2, since. So it doesn't matter what it did between those. It just, at the end, just like the fundamental theorem of calculus, it doesn't matter what it went through. You just do the function evaluated at B minus function evaluated at A. Same idea here. So what is f of 2, 1? So this problem's nice in that it's already given us f, and then it's already evaluated r for us. All we have to do is plug it into 2 to f. So it would be cosine pi x, so it would be cosine of 2 pi, plus sine of pi y, so it would be sine of pi times 1, minus x, y, z, so x times y times z, what's that? Minus -2. And then over here, same thing, plug in the 1/2 and 2 for x, y, and z, so it'll be cosine of pi, since x is 1, sine of 1/2 pi, or pi over 2, and then minus x, y, z, so is that -1? With me there? See where I get all those? Just plug it in. Cosine of 2 pi, that's all the way back around, so that's same as cosine 0, so that'd be 1. Sine of pi, well, that's also, well, it's 180, so 0, so y value, plus 2, then minus cosine of pi, so that would be -1, sine of pi over 2, positive 1, minus 1. See if you believe that. So it's, just cancel. Looks like it's 4. So anyway, that's not really, I guess we have kind of done some calculus there, but not really. It gave us what we need to do. We'll have to do calculus to get, but anyway, it's just pointing out, this type of problem is just pointing out, it doesn't matter the path. You just do f at the end point minus f at the end point. F at the terminal point minus f at the initial point. That's a better way to say that. All right, now, path doesn't matter. It doesn't, now this is, it is a special type of function really that we're dealing with here. This gradient vector, we have to be able to find the function associated there. So, we're starting basically with the gradient here. We need to find the function, so find the potential function. So it's not all, this isn't true for all line intervals. We'll talk about it. Okay. And that's what we're going to do here next, just some definitions. Just write those down just to. All right, F is, we talked about this one. A vector function is conservative. F is our general name, I guess. This is one we talked about, but just a reminder. If there is a function F such that F equals the gradient of F. That's that idea of conservative. That's number one. Number two, the line integral over C F dot dr is independent of path. So this is a new word here. If the line integral C1 F dot dr equals the integral over C2 F dot dr for any paths, C1 and C2. In D domain with the same initial and terminal points. Makes sense, okay? It's independent, doesn't matter the path. That's sort of what we were alluding to earlier. So that line integral, yeah, so the line integral, gradient of f dot dr, that is independent of path. For an example. Because like we said, it didn't matter where you evaluated it, what path it took. And if f is conservative, then, so kind of a corollary, I guess, if f is conservative, kind of combine the two here. If f is conservative, then the line integral f dot dr is independent of path. So those are conservative when we talked about independent of path. A little something different, but hopefully makes sense a little bit. Number 3. C is a closed path if its initial point and terminal point are the same. Closed path, if its initial point and terminal point are the same. Yeah, that's, so if I start here, my initial point, and then wherever it goes, if it comes back to that same point, yeah, it's closed, all right? That's a fairly simple example, but that's the idea. I mean, it could be three-dimensional, same idea, but you can see why we say that's closed. Fourth is simple. C is a simple path if it doesn't cross itself. C is a simple path if it doesn't cross itself or intersect itself. So is that path I drew, is that a simple? Yeah, it didn't cross itself, so it's simple. So what you don't, for simple, wherever you start, here, and then you go something like that, that's not simple. It's closed, but it's not simple. So it's just an idea. That might come up. All right, so then 5, region D is open if it doesn't contain any boundary points. So region D, again, for two-dimensional, all right, so let's say I've got this region D here. Well, usually if you do dotted lines, that means the boundary is not included there, and so that would be an open region. And then again, talking about the region D is connected. I mean, these are probably makes fairly good sense, but I just want us to make sure you understood them. Region D is connected if we can connect any two paths in D, any 2 points in D, sorry, with a path completely in D. Again, these aren't, any remarkable ideas here, just giving a name to it. Region D is connected if we can connect any 2 points in D with a path completely in D. So the idea here is, if I've got, here's my D. Simple one. So there's a point, any other point, so I can go from point to point completely in D. All right, so even if I do something maybe a little more complicated, that's still connected because I can go from this point to this other point somehow, just one way at least, by staying in the region. So where you would not have connected would be like if D is like a donut, I guess, or something. It's got a hole in it. So let's say that's my D, and then, well, it doesn't have to have a hole in it. So let's say region D, an obvious one. All right, so let's say that's region D where you got 2 parts. There's no way you can go from this part to that part inside D. You see, not connected. So again, it makes sense that that's what it's called because those aren't connected. But simple. And then 7. So connected, you could have a hole. So this still would be connected. Even if you have a hole in it, that's still connected because even though you can't go straight across, you can still go to any other point in there. So that's still connected. These 3 would be connected if there's 3 separate ones. These 2 are not connected. If that's one particular region, hopefully. I'm sure what I meant there. All right, so simply connected means connected, but with no holes. So, if I numbered them here, 1, 2, 3, region, D's. 1 is not simply connected, but it's connected. 2 and 3 are connected, and they are simply connected. So, does that make sense? Okay. Okay, and then a couple other little facts here. If line integral f dot dr is independent of path, then the line integral is equal 0 for everybody. So if it's independent, it's conservative. If it's conservative, Going back, well, yeah, if it's independent, it's conservative. And if it's conservative, then we have that potential, it's a potential function there. We're talking about, so it has a gradient there, and we just talked about the fundamental theorem of line integrals. You just take the, if it's a closed, and if it's closed, I forgot. I said it, but I didn't write it. For every closed path, yeah. Because remember, independent means conservative, conservative means you got this gradient vector, and it equals the function evaluated at RB, the endpoint of your path, minus f, the initial point of your path. So why is this 0? If we can do this. It's a closed path. What does a closed path mean? Initial point, terminal point are the same. So this point and this point are the same. So f evaluated at this point minus f evaluated at the same point. 0, isn't it? 0. Okay. All right. Now, so those are just some facts, and just to be aware of, because those terms might come up.